Hello everyone, and welcome to another presentation on the 3-degree concept that I wanted to discuss with you all regarding our descent planning. What I want to do is to present my own mathematical simple explanation on why the 3-degree value is used, because many of us tend to wonder, why do we use 3 degrees and why not other values? So what we'll do, we'll embark on a very simple mathematical explanation using high school mathematics, actually, the branch of trigonometry, and then we will use figures that we often don't use in flight because they are too accurate, and as pilots we don't fly with calculators on our laps to use the scientific functions of a calculator. So what I'm trying to do here is to make you appreciate how the values you obtained from the calculator approximate to the values we can obtain using simple mental maths, doing the same operations in a calculator. Now if you ask why the 3-degree value was used, the number 3 was used, from my own research and from those of you who have read further, it is just for convenience. The shallower the angle for descent, we are risking terrain contact, and if we are very high or very steep angle, rather, let's put it that way, then we will be compromising a lot of speed and altitude trading. So the 3 degrees was assigned and chosen way back historical times, in historical times rather, that the 3-degree gave a very good ratio between lift and drag of an aircraft and also for passenger comfort. Further reading can be obtained through accredited websites on this, but the whole point of this presentation is to make you appreciate that when we use the actual exact mathematical methods to calculate heights using the 3 degrees, using a scientific calculator, it gives you approximately the same value as you get when you do mental maths using the number 3 alone. Okay, and what we will do, we will base our explanation first on trigonometry, okay, to make you appreciate the values we get when we use the 3-degree function with the tangent function. And then from there we'll explore some graphs, simple graphs, and then we are going to analyze an approach plate into Harare and how we can use this whole idea, this whole concept in working out altitudes we have to be at to give us a good continuous descent final approach profile. Okay, so let's go ahead and see some little mathematics. I'll try and be as simple as I can, and I'm hoping you'll understand this presentation and maybe clear off most of your doubts. Of course, more reading is needed. You are always welcome, and it's going to be to your own benefit to see other presentations from other authors on this platform as well as this one. So let's go ahead and start our presentation on why do we multiply by 3 degrees. Okay guys, so what we see on the screen here is a simple diagram. Let's start by first of all getting the basics in. So we should know, I'm hoping you'll be able to see the cursor here, we should know that 1 nautical mile is equal to 6,076 feet. Okay, people approximate it to 6080 feet. To be more exact, is 6076.1 something. So we'll use 6076 as our value. Now, we all know, it's quite obvious, those of us who fly, that we are always going to be descending in a slanted manner. So slanted manner. We're not helicopters. This is not to do with any helicopters, which can descend vertically and also lift off vertically. Normally when a plane comes into land or comes in on an approach phase or a descent phase rather, it's always going to be in a slanted manner. So from your high school mathematics, we are looking at a right angle triangle, okay? A right angle triangle which forms a certain angle between the flight path, the standard flight path, and the horizontal distance from a particular waypoint or from the airport for that matter. So from your basic trigonometry, you know that there is sine, cos and tan. We are not interested about sine and cos in this case. We are interested about the tan function or tangent function. And without going too much into detail of teaching you that, which is of course a high school concept, we should know that the tangent or the tan of an angle is equal to the opposite side to that angle divided by the adjacent side of that angle. So tan is equal to opposite over adjacent, which we very well know. The mnemonic SOHCAHTOA is normally used in high school, for those of you who can recall your high school days. Me, myself, being a teacher of mathematics, still being an active teacher of mathematics at high school level, I still do these things almost every time with students. But for those of you who have forgotten, it's a very important little thing, maybe just to get a little textbook and recap on your trigonometry on the tangent of a right angle triangle. So the angle we are discussing here is 3 degrees, which is this angle here between the horizontal and the flight path of the aircraft, and the tan of that angle is equal to the opposite, which is the height, the vertical height in our case, divided by the distance from the reference point or from the airfield, from where you want to calculate. Okay, so that's going to be our opposite and that's going to be our adjacent. Right, now what we're going to do here, we have to appreciate one very important fact, a concept of this mathematics. Whenever you'll be multiplying large numbers by the tangent of 3, okay, the result that you get will be the same or similar, but very much the same as multiplying the same numbers by 3. Okay, but the same number, what I mean by the same number is that let's say if what we'll do, we'll see the graphs. I won't show the table. I don't want to say anything now. Let's just go and see the table that I've made, and then I'll explain to you what I mean by this this statement. When d is very large, meaning that when this distance here is very large, when you multiply that very large number by the tangent of 3, it's the same as multiplying by 3 alone. Okay, so d and h should be in the same units. That's very important. Now, if you are a pilot, for which this presentation is based for, height is measured in feet, but distance is measured in nautical miles. Those two are very different units, as you can appreciate. The height is measured in feet and the distance is measured in nautical miles. So the distance in our case should be converted to nautical miles. Excuse me, the distance should be converted to feet, which means that whatever the distance value is in nautical miles, we have to multiply that by 6076 to get the feet value. So which means that we can have feet here, which is already meant to be obvious. The height is always measured in feet, and the distance should also be measured in feet because it is nautical miles for the purpose of our calculations. Okay, I will make you appreciate that multiplying the distance in feet by tan 3 is the same as multiplying the distance in nautical miles by 3. I'll say it again. the distance in nautical miles times 3 is the same as the distance in feet multiplied by tan 3. Okay, that's very important. So make sure you record or replay this and understand what I'm trying to tell you. And this is our conversion from nautical miles into feet. Okay, so now having said that, I'm just going to be scrolling down. What I've done here is to make you appreciate the values. Okay, so let's say, for example, we are 3 nautical miles, 4 nautical miles, 5, and so on from a particular reference point. Let's say a center fix of an ILS approach, or a waypoint for that matter. Let's, for example, look at these values. So if you are 3 nautical miles, 3 multiplied by 6076 is going to give you 18,228 feet. Okay, and then if you want to work out the height, if you remember, if you make height the subject of our formula, height will be equal to the tan 3 times the distance times 6076 feet. Let me go back to the diagram. Okay, so here we are. The distance here is 3 nautical miles, this distance here. Okay, and 3 nautical miles is giving us 18,228 feet. So this here is 18,228 feet. Now if you want to work out the height, height is equal to distance times tan 3. If you can see, if you make height the subject, it will be distance times tan 3. Simple basic mathematics of transposing subjects from an equation. Basic algebra for you. Okay, so to work out the height, you multiply tan 3 by the distance in feet. Okay, which is what I've done here. And when you do that, you get 955.29. Now such numbers are very, very precise in a sense to use, which is also very good. But as I said, that we don't actually work with a calculator on our lap, so each time we want to work out values, we go and punch in calculator keys, because the aircraft is flying and we need to have, all pilots need to have what you call rules of thumb, which experts have formed. Okay, and they very well work to a very, very good degree of approximations, and are pretty much accurate for the flying case. So now you can see that I'm going to get 955.29. Now if I do the same calculation now, the distance, this time in nautical miles, remember this one was in feet. Okay, so it's in feet times 3. In feet times 3 gives you times tan 3 rather. In feet times tan 3 gives you that. In nautical miles, 3 times 3 gives you 9. Now from the people who have actually come up with this, they saw a pattern which I'm trying to show you here. If you take these values which you get by multiplying the distance nautical miles by 3, you get all these values here. Then you can add 2 zeros to make them into hundreds. Okay, so 3 times 3 is 9, with 2 zeros added will be 900. 4 times 3 is 12, with 2 zeros added will be 1200, and so on and so forth, if you can see what I'm doing here. Okay, now if you carefully look at 900, we know we don't often use 900, but the best figure to use is 1000. So an additive is very important. This is what I have come across to explain to you. So each time I'm doing here a calculation, if you can see, 4, let's say for example 4 nautical miles. 4 nautical miles in feet multiplied by 6076 is going to give you 24,304 feet. Okay, and when you want to work out the height corresponding to 4 nautical miles distance, if you go to our formula, it's going to give you 1,273.2 feet using this calculation here. Okay, now if you do the same 4 times 3, you're going to get 12. Add 2 zeros, it gives you 1,200. Now if you look at this figure here, is 1273. To the nearest 100 is going to give you 1,300. Okay, you can clearly see that if I just add 100 feet to this, I'm going to get this figure here. This figure here will be the same as this figure here. You can see, you can appreciate that. Similarly, the same thing for this figure here, for example, for 5 miles, will be to the nearest 100 is going to give 1,600. So now you can clearly see that we are breaking down our workload. Instead of using calculators, we can easily do a little bit of mental maths. So you can see all these are coming to a reasonable degree of approximation. They may not be exactly the same, but they do give you the clearer picture of what you want. I've highlighted these here because these ones to the nearest 100 was giving us at least a bit more than what I was expecting, because here is 2800, 2900. So these two are a bit more of, we just add maybe 200 feet, 100 feet here rather, and maybe 200 feet here, because 3184 is for 10 miles. 10 miles times 3 is 30. Add 2 zeros give you 3000, and this to the nearest 100 is 3200. So 10 miles onwards, we add, let's say, 200 to the values we get in this table here. I hope that is making sense. One more just example I can give you, let's say 7 miles, for example. So 7 miles, okay, in feet is going to give you 42,532 feet, okay. And then if you want to talk about the height corresponding to 42,532, you can use the calculation in the column here, okay, and you get 2229.01, okay. That's a very exact, precise figure. However, if you do 7 again, 7 times 3, there it is, times 3 gives you 21, okay, and then 21 add 2 zeros gives you 2100. However, if you see this figure here is mostly 2200 then 2100, so we just add 100 here. So what I came across here is that anything maybe, let's say, more than 6 nautical miles, we can add an extra 100 feet, okay, or 5 miles, the same thing as well. An extra 100 feet is very important because it gives you a bit of a clearance, okay, a bit of a clearance from the ground. So 900 plus 100 gives you 1000, 1200 plus 100 gives you 1300, 1500 plus 100 gives you 1600, 1800 plus 100 gives you 1900, and so on and so forth. So now you can appreciate, once more I will say it very slowly, if you multiply the distance in feet by tan 3 is roughly equal to the same as multiplying the same distance by 3, add 2 zeros, and add an additive of, let's say, 100 feet. Okay, so what we normally use in flight, we won't use this method here in this column because this is too precise and needs a scientific calculator. However, we will just say, okay, I want to be at 3 nautical miles, or I want to be at, let's say, 5 nautical miles. What do I do? Okay, I'll do 5 times 3, I'll get 15. Add 2 zeros gives me 1500, and add an additive of 100 feet gives you 1600. So from if I'm working backwards, I will add 1600 to the altitude where I have to be at to see where I'm going to start my descent from. Now the last column here, you can see, is giving you a very important analysis. If you divide, okay, all the, if you divide the values in this column, okay, by the values in those columns, okay, you are going to get tan 3 all the way. Okay, it's very important that you understand that this is a very important analysis, that I want you to understand this. Okay, so the value of tan 3 is 0.05. okay, and if you divide, let's say, these additives here, for instance, all these additives here, okay, which are also in feet, by these ones here, which are also in feet, okay, you are going to get 0.05. So if you do 1300, let's say, for example, divided by 24304, you're going to get this, and so on and so forth. So this tells you that all these are obeying the 3-degree profile. Okay, that was quite a bit to digest there, but I'm hoping that you'll understand. You can also take a screenshot of this table. It's very important that you study it and you can make comparisons of the relationships as we go along. Okay, I want you to understand this carefully, and then we can move on now to plot some little graphs, and I want you to appreciate how this whole thing comes about. So let's go and see. Just ignore all these pages for now, they're just an error. What I've done here now is that I've tried to produce some graphs. I have made a graph of the vertical height against the horizontal distance. So this first graph which you see here is when we don't have any additives. So it's going to be the vertical height, okay, vertical height, which is going to be this column here, okay, height, versus this column here where we don't have additives. Okay, that's very important. So it's going to be this height column here versus that column there. And if you see the graph, it's quite a bit messy. It's not very straight, it's not very linear. It is linear in some cases, but it's not exactly linear. So you can see there are some kinks which we have here, which is very good. However, what I did next is that when I now plotted the same vertical height with the additives, okay, with the horizontal distance, okay, with the 100 feet additives, you can see now the graph was becoming a bit more straight. Okay, so this time what I've done, I have computed on the y-axis the vertical height with the additive, which is this column here, not that one there which was on the first one, but this column here with the distances. And then what you have seen is that the graph was very much linear. Okay, it was following a very much linear pattern. The trend line, which is in red here, and the actual line of the graph are pretty much close to each other. At some points they're also overlapping each other. Okay, now I want you to compare this graph with this one here, which is the graph of the exact values. Now these are actual values of D and H using the 6076 and the tan 3. And now if you see this graph and this graph here, they're more or less the same, okay, and giving you a 3-degree profile. So this is where I wanted to appreciate, okay, that the additive is very important, because the additive is going to bring you closer to the actual, okay, actual computations that you would do with a calculator using the actual figures. Okay, so the additive is there as a very good approximation. So normally when we go back on this table here, I want you to appreciate the fact that this additive is very important. So let's say you want to be at 6 miles from a particular fix. 6 times 3 is 18. Add 2 zeros and just give it 100 feet. So 1900. Okay, and so on and so forth. This will keep you safe from terrain as well. You won't be too low. You will be at a very convenient profile. I'm hoping that so far this is making sense, and if so, then what we can do now is that we can continue to proceed onto the approach plate into Harare. So what you see on the screen here is just part of the approach, ILS approach into Harare. Okay, I want to explain to you this concept of working out our 3-degree profile. So as I said, that it's not a lesson on explaining approach plates, but still more we can still talk about what we're going to do. So say for instance we want to do a full ILS approach. I'll just zoom a bit so you can see what's happening here. We are coming in from the northeast. Say for instance we're coming northeast, so we're coming in from this direction here. Okay, we're going to go overhead the Victor Hotel Alpha VOR, and then we're going to go continue straight down, overhead the Sierra India NDB, then the Oscar Lima NDB, from where we will continue slightly, and then we have to make what you call a procedure turn. And from your IFR notes and lessons, you know what I'm talking about here, to intercept the ILS profile all the way down to the landing. Okay, now we always do what you call continuous descent profiles, meaning that we don't want to level off. Even though here it says we can level off at the outer marker, I mean the Oscar Lima at 7,000, and all the way here, from here 7,000 all the way into this procedure turn until we intercept the glide slope at 7,000 feet. We have to be level. That is okay, but still more, looking at fuel consumptions, we avoid such such flying. So what we do, we compute a continuous descent final approach profile. Okay, and that's where the 3-degree and the number 3 comes into play. All right, now let's see what we how we can program our FMS. Okay, our FMS actually gives you a profile as well, and I'll also show you just below on what the FMS in the Q400 was showing when I programmed the ILS approach into Harare using the FMS alone, and then we can take it from there. So let's look at what's happening. So if you have this, I want you to have this picture, maybe screenshot it or keep it somewhere so that at least I can explain to you the following slides. You know, my presentations are not very fancy. I don't have that much of facility to produce very fancy presentations, so sometimes I just tell you to keep this in store, part of it in store, so that you can refer to it in the subsequent explanations. Now, if you look at the sequence, we are coming from northeast. It will be we're going to go over Victor Hotel Alpha. Then we're going to go overhead the ILS intercept, which is 10.5 nautical miles, or roughly say 11 nautical miles from the Victor Hotel Alpha. So if I go back, the FMS is calculating for me from Victor Hotel Alpha. I ignore all these points here. I'm working at this point here. That's my first point. After Victor Hotel Alpha, I'll go to this point here. Okay, 10.5, which it says here 10.5 nautical miles. That's an intercept point. But notice that I'm not intercepting it, not yet. I'm going to be above the 7,000 feet that I need to intercept it. Okay, and then from there I'm going to go into the procedure turn until another point, which is 12 nautical miles Victor Hotel Alpha, which is opposite the waypoint called Hydro. This will be in the turn. So if I go back here, that point will be somewhere here on this leg, on the 45-degree leg. You must know that this is a 45-degree teardrop sector. Okay, this is 232, that's 187, that's 45. So somewhere here is a 12 nautical mile point, which the FMS will calculate. After that, I'm going to continue on this loop until I intercept, until I go to Hydro. So my next point in the sequence is going to be Hydro, which is also 12 nautical miles. It's symmetrically opposite with this one here. And then, once again, as I'm descending, I'm going to go and intercept the ILS intercept, this time at exact 7,000 feet. You see, it was also here, but remember, we were higher. We had to be high here, so we are continuing to descend. And then we intercept it here on our final shot at 7,000 feet. Okay, now, let's see what the FMS looks like for these things. If you see, this is the part of the FMS screenshots that I've taken. Forget about the Kobod. Kobod is just a waypoint. We're coming in from Lilongwe. Okay, we're going to go to Kobod. Then we're going to go to a point which is, because we're coming in runway 23 straight in, but then we're going to make a procedure for ILS runway 05, which is a reciprocal. Okay, so we start from here. The FMS is calculating these values. So Victor Hotel Alpha, we have to cross at 12,343 feet. Then we go to CF05, which is the intercept, which I showed you in the table here. I want you to also keep this one here. That's a CF05. Okay, we have to be there at 8997, and then we make a procedure turn. In the 45-degree leg, we will be intercepting the Victor Alpha 12 mile point at 8226. And then from there, we're going to go to Hydro, which is 7584, and then we're going to intercept the ILS at 7116. You can see all these figures are very high. These figures are very high because the plate wants you to intercept the ILS at 7,000 feet, whereas the FMS is going to make you intercept the ILS at 7116 feet. So you'll come quite high. Okay, so now the question is, how do I program a smooth continuous descent final approach 3-degree profile? Okay, so let's have a look at that. If you look at the FMS profile here, which I've done here, Victor Alpha and all these figures that the FMS gave us, if I work out the total profile using my trigonometry, okay, the difference between 12,343 and 7116 is giving us 5227, and of course this point here is 10.5 miles from Victor Alpha. Let's go back to the page so I can show you. So this point here where we intercept the ILS is 10.5 miles from the VOR Victor Alpha, and if you multiply 10.5 by 6076 feet, you get 63798. Once again, if you go all the way to your formula here, if you want to work out the tan, of this angle, or this angle rather itself, okay, this angle itself is going to give you 4.7 degrees. So you can see it's approximately 5 degrees, and it's quite a steep approach. Okay, not that steep, but it is steep. So you don't want that sort of approach for now, for convenience purposes. The FMS has given it to you, fine, but we are always able to input our own values which can suit our own descent profile, as long as we don't compromise safety and we don't conflict with any terrain clearance values. Okay, so as I've said here, this gives a slightly high continuous descent profile, so we must adjust the values to suit a 3-degree profile. We need to intercept the CF center fix at 7,000 feet, and at hydro we must also be at 7,000 feet. Now we're going to start working backwards. So we're going to work from right to left, meaning we're going to start calculating from here. We have to be at 7,000, here we have to be 7,000 as well. So we're going to go all the way back using our 3-degree rule that we've been discussing, and the table will be also going back and forth to see what's happening. So I'm now going to draw the same profile, but now with a shallower 3-degree angle. Now at CF center fix, intercept point for the ILS for runway 05 in Harare, we have to intercept at 7,000 feet as per our approach plate, as you might recall. At hydro as well, we have to be at 7,000 feet. Now let's look at the distances. From the center fix to hydro is 1.5 miles. Okay, we can work that out like this. I'll go back and forth so that you understand what I'm trying to say. So here's a plate. Hydro is 12 miles from Victor Hotel Alpha, and the center fix is 10.5 miles Victor Hotel Alpha. The difference is 1.5. Okay, that is done. Now let's look at other distance here. So from hydro to the Victor Hotel Alpha 12 nautical mile is 2 nautical miles. Okay, that's the whole loop. And from Victor Hotel Alpha to the center fix again is 1.5 nautical miles, and then from the center fix to Victor Hotel Alpha is 10.5 nautical miles. Okay, so now let's look at these distances on our plate. From the 10.5, I'm working backwards now. From 10.5 miles to hydro is 1.5. From 10.5 miles to the Victor Hotel Alpha here is also 1.5. So this is 3 nautical miles. That's 3 nautical miles. Now this whole teardrop here is meant to be 5 nautical miles in length. No, sometimes it's 10 nautical miles. This is 5 nautical miles in length. Okay, so the remaining distance here from Victor Hotel Alpha 12 miles to hydro is going to be 5 minus 3, which is 2 nautical miles. Okay, I hope that makes sense. So if you see this distance here, I gave it 2 nautical miles, which is from hydro to the Victor Hotel Alpha 12 nautical miles point, which is on the 45-degree leg. Okay, now what we do, we don't use decimals as such, as you might be aware of in mental calculations. So 1.5 approximates to 2 nautical miles, and 10.5 approximates to 11 nautical miles. So if I start working backwards, I want to be at center fix 7,000 feet, and so I also want to be at hydro 7,000 feet. So I'm going to program these altitudes in the FMS next to center fix, the last one, and hydro. Now I want to know how high should I be at this point here, which comes before hydro, this point here. How high should I be there? Well, I will take this distance here, 7,000 feet, and I'll have to add to it another height. What will that other height be? Well, this is 2 nautical miles, right? And from our table explanation, 2 times 3 is 6, add 2 zeros, and it gives you 600. So I can say I'm going to cross this point at 7,600. Okay, now, fine, fair enough. Now I'm still going backwards because I want to know my final calculation should be at what height should I be crossing Victor Hotel Alpha to now start following the full ILS procedure. Alright, so from here I have to cross first of all the center fix again, but at a higher altitude. So now I look at this distance here. Okay, 1.5 nautical miles, approximately 2 nautical miles again. Okay, and 2 times 3 is 600. So I'm going to add 600 this time to 7,600 to give me 8,200. Okay, And then from the center fix of the Victoria Alpha is 10.5 miles, call it 11 miles. So 11 times 3 is 33, maybe 33, and you can just add 200 feet. Okay, as you can see that the higher, if you go further out, you can add maybe a bit more of an additive. So 11 times 3 is 33, add 2 zeros give you 3300, and then you can add 200 feet to give you 3500 roughly. Okay, and then you add 3500 to 8200, and it's going to give you 11,700. So now working backwards, that's what it gives us. Now if you program the FMS in this sequence, it should give you a very good continuous descent profile. Okay, so 11,700, 8,200, 7,600, 7,000, 7,000. So I'm going to come all the way from the northeast. I will program here 11,700, okay, and then 8,200, 7,600, all the way to 7,000, hit hydro, level off for maybe a little bit, and then I intercept the ILS at 7,000, okay, which means that in the FMS now, here I'm going to have line select keys where I'm going to put 11,700 here, 8,200 here, 7,600 here, and 7,000 at hydro, 7,000 at the center fix. This is going to give me a 3-degree profile all the way down to intercepting the ILS approach, and then after that the ILS itself is calibrated as 3 degrees anyway, so I don't have to worry about it too much. I hope that this idea is making sense on the mental maths concept, using the mental maths concept with the digit 3 and using the precise figures with the scientific calculator using the tangent of 3 and the like. The whole purpose of this exercise was to make you appreciate that multiplying 3 to a number is the same as that number changed to feet, which gives you a very large number, and multiplying it by tan 3. Okay, so it's almost the same, and you just have to cater for some additive, and you should be quite okay to use this rule for your descent planning. I am hoping that you'll listen to this a bit more and more again, so that you understand the whole concept. You can drop any comments or questions that you might have, or even your own suggestion opinions, as we're always welcome, as we are as aviators, we're always learning from each other, and I really appreciate your own feedback. That was it for now for this presentation. I hope you have learned something, and please don't forget to subscribe. So I'm trying to make some more videos for you. The more I learn, the little I learn, and my own understanding, I'll be sharing it on this platform. Thank you very much, and happy landings to all of you, and be safe as always. Please be safe. Thank you.